Having studied the mechanism of hemiacetal formation and acetal formation, we now have to consider the mechanism of the reverse reactions, namely the hydrolysis, first of hemiacetals and then in the next video of acetals. I always tell my students you need to know these mechanisms backwards and forwards. So we did them forwards, and now we're going to go ahead and do them backwards. So hydrolysis, it literally means breaking apart lysine with water, hydro. So reaction of a hemiacetal with water under either acidic or basic conditions results in hydrolysis of the hemiacetal to generate a molecule of aldehyde or ketone and a molecule of alcohol. So you can see an example here, the hemiacetal reacting with water to give acetone in this case, plus a molecule of methanol. Now the mechanism of this reaction is essentially the exact reverse of hemiacetal formation. So let's give it a look. We will first look at the mechanism under acidic conditions, and then we'll look at the mechanism under basic conditions, because as I said, this reaction takes place under both sets of conditions. So under acidic conditions, the first step is protonation of the ether oxygen to make it into a good leaving group. As you remember, a hemiacetal has an alcohol and an ether bound to the same carbon. In order for it to hydrolyze, we've got to get the the ether fragment that's going to eventually become an alcohol when the reaction is done. We have to get the ether fragment off. If we're going to get it off, it's got to become a leaving group, and in order to be a good leaving group, we've got to protonate it. So that will happen under aqueous acidic conditions, H3O+, and now we have the protonated ether. Step 2 is loss of the neutral alcohol now. So the protonated ether is lost as a neutral alcohol as the leaving group. So methanol has now been jettisoned. It's the leaving group, it's left. And what we are left with is an oxocarbocation, because when you break that carbon-oxygen bond, put both of the electrons onto the oxygen, you are left with a positive charge on the carbon. Now note that the oxocarbocation has another resonance structure. And in the other resonance structure for the oxocarbocation, in which the positive charge is on oxygen, this second resonance structure is simply a protonated carbonyl group. So then step 3 is simply deprotonation of the cationic oxygen to yield the neutral ketone. Okay, so a couple of notes that I want you to take home from this mechanism. First of all 3 steps are reversible. They have equilibrium constants very close to 1, so therefore I am drawing equilibrium arrows instead of just forwards arrows in these steps. And then second of all, the base that I am using to deprotonate in the final step is water, because water is the strongest base that can be present under the acidic conditions that this mechanism is taking place under. Now I'd like to look at the mechanism under basic conditions. Under basic conditions, we're going to have minus charges on the intermediates. We will have strong bases present. So the first step is to use hydroxide as a base to deprotonate the alcohol part of the hemiacetal. So in the acidic mechanism, we protonated the ether fragment. In the basic mechanism, we start by deprotonating the alcohol fragment. That proton transfer reaction is going to require 2 arrows, one to remove the hydrogen from the OH, and then the second arrow from the bond to the oxygen. Then once we have deprotonated the alcohol, we've generated an oxygen with a negative charge on it. What it wants to do now is regenerate the carbonyl group. So it's going to take the extra electrons that are on the oxygen, take 2 of them, use them to form a carbon-oxygen pi bond. Now, if you're forming another bond to the carbon, you also have to break a bond to that carbon, because the carbon already is forming 4 bonds. If we just formed another bond without expelling something as a leaving group, we would have 5 bonds to carbon. So the leaving group here is methoxide, CH3O-. Now, you may be thinking in your head, I can't do this, that's not a good leaving group, it's a strong base. Well, in this reaction, it's okay to have a strong base as a leaving group because the reaction is taking place under strongly basic conditions. So as long as you have a base as strong as OH-, kicking out OCH3- is not kicking out a base that's any stronger than the base that we are using to start the mechanism. So in this case, under basic conditions, methoxide is fine as a leaving group. So we've generated our carbonyl compound. We are almost done, except when you looked at the example of the reaction, you saw that we generated an equivalent of alcohol and not an equivalent of alkoxide. So the final step of this is simply a proton transfer reaction. I'm not drawing out all the arrows for this step, but CH3O- gets protonated by water. Again, this is a reaction, an acid-base reaction, with an equilibrium constant very close to 1, so we're drawing this with equilibrium arrows, to generate as products methanol, neutral, organic is neutral, and regenerating hydroxide, which is what we used in the first step of the mechanism. So therefore, just like only a catalytic amount of acid is necessary for the acidic mechanism, only a catalytic amount of base is necessary for the basic mechanism. In the next video, we'll take these ideas one step further and talk about the hydrolysis of an acetate.